For over 50 years, the surface of the moon was just a distant memory. But tonight, it officially becomes an industrial frontier. This shift began behind the sealed doors of an agency in crisis. In 2025, NASA experienced its largest single-year staff departure in history, a 20% exodus that threatened the continuity of the entire program. Years of treating spacecraft as bespoke, handcrafted projects meant major launches were separated by long intervals. During these gaps, the core competencies required for high-frequency spaceflight began to atrophy within the civil servant workforce. Artemis II served as the primary mechanism to halt this institutional collapse, forcing the agency to reintegrate its ground and flight operations under the pressure of a high-stakes, crude deadline. That reintegration was led by the 15th Administrator, Jared Isaacman. Confirmed in late 2025, he arrived with an entrepreneurial mandate called Back to Basics. He moved to end the era of artisanal vehicle construction, demanding a shift toward a standardized, high-cadence launch model that prioritized repeatable operations over one-off technical demonstrations. Isaacman's strategy targeted a specific economic threshold, reducing launch costs through standardization until the value of resources harvested from the lunar surface could eventually offset the expense of reaching it. This doctrine transformed Artemis II into the ultimate trial by fire for NASA's new operational philosophy. On April 1, 2026, the Space Launch System lifted off from Pad 39B. Producing 8.8 million pounds of thrust, the vehicle validated the Block 1 configuration as the only current system capable of sending crew and cargo to the moon in a single launch. To protect the infrastructure for future missions, engineers modified Pad 39B with flexible gaseous distribution panels. These components were designed to flex under the intense acoustic energy of the liftoff, allowing the pad to remain operational with minimal post-launch repair. This animated diagram compares the spacecraft's re-entry profiles. To address the heat shield charring seen on previous missions, planners utilized a steeper descent angle. This trajectory reduced the total time the capsule spent exposed to the most intense thermal environments. Looking at the data here, post-flight inspections confirmed the success of the new profile. The chart shows a significant reduction in both the quantity and size of char loss compared to the Artemis I baseline. Proving the heat shield could withstand these conditions was a prerequisite for moving the Orion hardware into the high-cadence operations Isaacman demanded. Within the cabin, the crew faced the immediate logistical challenges of deep space survival. Shortly after launch, an anomaly was detected in the urine vent line, threatening the hygiene of the small living space. In a pressurized environment, a malfunction in waste management risks contaminating the cabin air and damaging sensitive electronics. A complete failure in this system creates a direct threat to primary life support. Mission specialist Christina Koch coordinated with ground controllers to troubleshoot the hardware while the spacecraft was traveling at 25,000 miles per hour, eventually restoring the system's function. Once past the Earth orbit verification phase, the spacecraft reached Pericentheon, surpassing Apollo 13's distance record. From a 4,000-mile altitude, the astronauts had a clear view of the lunar poles and Vavilov crater, capturing high-resolution data for future landing missions. As they rounded the lunar far side, the crew witnessed Earthset, watching the entire planet disappear behind the moon's edge while they remained cut off from all communication with Houston. The logistical struggle to maintain biological life inside a metal box highlights the high stakes of this transit. It is the reality of a species attempting to establish a permanent presence on a second world. While the astronauts were behind the moon, NASA leadership initiated a fundamental shift in the program's roadmap, a move known as the Isaacman shock. This schematic illustrates the strategic change. It involved the sudden cancellation of the Lunar Gateway, an orbital station that had been a cornerstone of the architecture for years, to prioritize a direct-to-surface approach. This created an immediate culture shift within the agency. Engineers were moved from a decade of methodical, infrastructure-heavy planning into a high-speed, entrepreneurial rhythm focused on immediate surface goals. Allied partners like the European Space Agency and Japan's JAXA faced a sudden diplomatic crisis as their multi-billion-dollar investments in orbital modules no longer had a primary destination. The geopolitical pressure to reach the surface before 2028 effectively dismantled years of international space policy in favor of architectural speed and surface dominance. This standardized architecture is intended to catalyze a commercial expansion by 2028. Without the requirement to dock at an orbital station, commercial partners like SpaceX and Blue Origin can ferry cargo directly to the lunar surface with increased frequency. The cancellation has also prompted a reaction from middle power nations. Canada and members of the ESA are now exploring independent consortia to ensure their lunar hardware remains relevant in a surface-first environment. The funding redirected from the Gateway is now focused on a 2030 objective, a permanent surface base equipped with its own nuclear reactor. The successful 10-day flight of Artemis II validated the hardware required for this transit. With the focus now squarely on surface habitats and power systems, the mission confirmed that the return to the Moon is no longer a rehearsal, but the start of a permanent residence on another world.
An investment in knowledge pays the best interest, so why not invest in this channel? Click like and subscribe for more.